Subscribe to the channel so you don't miss out on any of these videos. It's hard to imagine the universe as anything but calm and serene when you look up at the night sky, but beneath that peaceful blanket of stars lies a drama of unimaginable scale and intensity. Picture this: in the vast darkness of space, a newborn star is fighting to claim its place in the cosmos. And as it grows, it unleashes something extraordinary: colossal streams of energy and matter, ripping through the surrounding gas and dust like cosmic lances. These are the polar jets of protostars, some of the most mysterious and awe-inspiring phenomena in the universe. What are they? Why do they form? And how do they shape the universe as we know it? The answers may not just rewrite what we know about star formation but could reveal secrets about the very nature of space itself. Let's start with what's happening at the very beginning of a star's life, in the heart of a cold, dark molecular cloud. These clouds are the cradles of stars, vast regions of gas and dust where gravity begins to gather materials into denser and denser clumps. Once a clump becomes dense enough, its core starts to heat up, sparking the earliest stages of nuclear fusion. This is where things get interesting. As the protostar forms at the center, not all the material around it falls neatly into place. Some of it gets caught in the chaos, spinning wildly and creating an accretion disk, a swirling plane of gas and dust orbiting the young star. The accretion disk plays a crucial role here, acting almost like a traffic director for all the material falling toward the star. But there's more to the story than just that. As the protostar spins, powerful magnetic fields form around it. These magnetic fields act like colossal slingshots, channeling energy and material away from the star and launching it out into space at nearly incomprehensible speeds. This is what creates the polar jets: two narrow, focused beams of energy and matter shooting out from the north and south poles of the protostar. These jets can stretch across light years, cutting through the surrounding molecular cloud like swords of light. Now you might wonder, why do these jets exist? Isn't the material supposed to be feeding the growing star? It turns out that the jets are almost like a pressure release valve for the protostar. Without them, the sheer amount of energy generated during star formation would overwhelm the system, possibly even preventing the star from fully forming. The jets allow the protostar to stabilize, ejecting excess angular momentum and energy into the surrounding space. Think of it like a spinning top shedding some of its speed to stay upright and balanced. But the polar jets are more than just a byproduct of star formation. They actively shape their environment. As these jets blast through the surrounding molecular cloud, they carve out enormous cavities, pushing away gas and dust and creating regions of higher and lower density. These interactions can trigger the formation of new stars in nearby regions by compressing the gas and dust into dense clumps. In this way, the jets don't just mark the birth of a single star. They can set off a chain reaction, influencing the birth of entire star systems. The sheer power of these jets is hard to comprehend. Some of them move at speeds close to a significant fraction of the speed of light, carrying enough energy to completely transform their surroundings. And they're not just made of ordinary matter. Scientists have discovered that these jets often carry high-energy particles, including electrons and protons, accelerated to near-light speeds. This high-energy radiation can have far-reaching effects, influencing the chemistry and structure of interstellar clouds far from the protostar itself. What's even more fascinating is that these jets seem to have a profound connection to some of the most extreme phenomena in the universe. For example, the jets of protostars bear striking similarities to the jets emitted by black holes and neutron stars. While the scales and mechanisms are different, the underlying physics, magnetic fields channeling energy and matter into focused beams, is surprisingly similar. This has led scientists to wonder whether studying protostellar jets could provide insights into these more extreme cosmic events. But despite all we've learned, the polar jets of protostars remain a deep mystery in many ways. For one, we still don't fully understand the exact mechanisms that generate and sustain these jets. The role of magnetic fields is crucial, but how these fields interact with the accretion disk and the surrounding environment is still being studied. Advanced telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope are beginning to provide more detailed observations, revealing the intricate structures of these jets and their interactions with the surrounding space. And then there's the question of how these jets evolve over time. As the protostar matures into a fully fledged star, the jets eventually fade away. But what happens to the material and energy they've ejected? Do they leave behind lasting imprints on their environment, or does the surrounding cloud eventually absorb and disperse them? These are the kinds of questions that keep astronomers awake at night, poring over data and simulations in search of answers. It's also worth noting that these jets might hold clues to the origins of planetary systems like our own. The accretion disks around protostars are not just the source of the jets, they're also the birthplace of planets. By studying how the jets interact with these disks, scientists hope to better understand how planets form and evolve. Could the polar jets influence the distribution of material in the disk, shaping the types and sizes of planets that emerge? It's a tantalizing possibility, one that could help explain why planetary systems come in such a bewildering variety across the galaxy. The story of polar jets doesn't end with protostars either. As we look further out into the universe, we see evidence of jets in countless other contexts, from the smallest brown dwarfs to the most massive black holes. These jets serve as a reminder that the universe is not a static place. It's a dynamic, ever-changing tapestry of forces and energies, constantly interacting and reshaping the cosmos. And while the polar jets of protostars may be just one piece of this puzzle, they are a crucial one, offering a glimpse into the raw power and complexity of star formation. The polar jets of protostars are a testament to the universe's ability to surprise and awe us. They are a reminder that even in the seemingly calm and quiet process of star formation, there is incredible energy and drama at play. These jets may be fleeting, lasting only a fraction of a star's lifetime, but their impact is profound, shaping the very fabric of the cosmos in ways we are only beginning to understand. As we continue unraveling the mysteries of polar jets, it becomes evident that these streams of energy are not merely a byproduct of star formation but play a fundamental role in shaping the interstellar medium. Imagine this. When a newborn star ejects its polar jets, it isn't just creating beautiful, luminous beams of light, it's actively sculpting the environment. The molecular cloud that birthed the star is no longer the same. Cavities form, shockwaves ripple outward, and complex patterns of turbulence arise, setting the stage for new stars and planets to emerge. One of the most fascinating aspects of these jets is their ability to generate shocks in the surrounding medium. When the jets collide with the slower-moving material in the molecular cloud, they create what are known as bow shocks. These are regions where the jet's supersonic material abruptly slows down, converting its kinetic energy into heat and light. Bow shocks are often visible in infrared wavelengths, glowing like celestial graffiti across the night sky. These shocks compress the gas and dust in their path, creating dense pockets that can trigger the formation of new stars. It's almost as if the jets are sowing the seeds for the next generation of stellar life. The polar jets are also a window into the early stages of a star's life, which are notoriously difficult to study. Protostars are shrouded in dense cocoons of gas and dust, making them nearly invisible in visible light. However, the jets punch through this surrounding material, creating bright, elongated structures that can be observed across multiple wavelengths. By studying these jets, astronomers can infer critical details about the hidden protostar, such as its mass, rotation rate, and magnetic field strength. But these observations are not without their challenges. The polar jets are highly dynamic, changing on timescales of years or even months. This makes them difficult to capture in detail, as each observation provides only a snapshot of a process that is constantly evolving. Advances in observational technology, such as adaptive optics and high-resolution interferometry, are helping scientists piece together these fleeting moments, creating a more complete picture of how these jets operate. A key breakthrough in our understanding of polar jets came from the discovery of their collimated nature. Unlike the chaotic outflows of material seen in some astrophysical processes, polar jets are remarkably narrow and focused, maintaining their shape over vast distances. This collimation is thought to result from the interplay between the magnetic fields and the surrounding accretion disk. The magnetic fields act as a kind of funnel, channeling the material into tightly constrained streams. Understanding this process is crucial because it has implications for other cosmic jets, such as those emitted by active galactic nuclei and gamma-ray bursts. One intriguing question is whether all protostars produce polar jets, or if they are a feature of only certain types of star formation. Observations suggest that jets are a common, if not universal, feature of protostars, appearing in stars of various masses and stages of development. However, the intensity and structure of the jets can vary widely. Low-mass stars, like our Sun, tend to produce more modest jets, while high-mass stars can generate jets powerful enough to disrupt their entire surroundings. These variations provide valuable clues about the conditions required for jet formation and the role of magnetic fields in the process. Another area of active research is the composition of the jets. While we know they consist primarily of ionized gas, or plasma, the specific elements and molecules within the jets can vary. For instance, some jets contain water molecules, which are thought to form when shockwaves heat the surrounding material. These molecules emit radiation at specific wavelengths, allowing scientists to map the structure and motion of the jets in unprecedented detail. Such studies are not just academic, they have practical implications for understanding the chemistry of interstellar space and the origins of complex molecules that may play a role in the development of life. The interaction between the jets and their environment is another rich area of exploration. As the jets carve through the molecular cloud, they create a chaotic interplay of forces, including turbulence, compression, and heating. These interactions can have cascading effects, influencing the formation of stars, planets, and even larger structures like stellar clusters. By studying these interactions, scientists hope to uncover the broader role that polar jets play in galactic evolution. Interestingly, the polar jets of protostars are not confined to the early stages of star formation. As the star grows and its accretion disk dissipates, the jets evolve, becoming weaker and more diffuse. However, their impact on the surrounding environment can persist for millions of years, leaving behind traces that astronomers can study long after the jets themselves have faded. These remnants, known as outflow cavities, provide a fossil record of the jet's activity, offering insights into the star's early life. On a larger scale, polar jets also contribute to the redistribution of angular momentum within the molecular cloud. This is a critical process because the initial rotation of the cloud could otherwise prevent the formation of stars. By ejecting angular momentum through the jets, the protostar allows more material to accrete, facilitating its growth and stabilization. This process is not only essential for individual stars but also for the formation of binary and multiple star systems, which make up the majority of stars in the universe. Despite these advances, many questions about polar jets remain unanswered. For instance, what triggers the initial formation of the jets? How do they maintain their incredible speeds and focus over such long distances? And what role do they play in the broader context of star formation across different types of galaxies? These questions drive ongoing research, as astronomers use increasingly sophisticated tools to probe the depths of these enigmatic phenomena. One of the most exciting prospects is the potential to simulate polar jets using computer models. By recreating the conditions of star formation in virtual environments, scientists can test different hypotheses about the origin and behavior of the jets. These simulations are incredibly complex, requiring vast computational resources to model the interplay of gravity, magnetism, and fluid dynamics. However, they offer a powerful way to explore scenarios that would be impossible to observe directly. Polar jets are a reminder of the dynamic and interconnected nature of the universe. They show us that even the most violent and energetic processes can have creative outcomes, shaping the cosmos in ways that are both beautiful and profound. From their role in star formation to their potential connections to the origins of life, these jets are a testament to the richness and complexity of the universe. The study of polar jets also opens doors to understanding broader astrophysical phenomena, as the underlying physics of these jets appears to resonate across a variety of cosmic scales. For instance, the mechanisms driving the collimation and acceleration of protostellar jets share striking similarities with those observed in the jets of supermassive black holes at the centers of galaxies. While the scales and energy outputs are vastly different, the processes involving magnetic fields, accretion, and angular momentum transfer create a unifying thread. This connection suggests that the universe operates on common principles, where the rules governing a tiny protostar and a distant nebula are echoed in the colossal structures of galaxy clusters. Another aspect worth delving into is the role of radiation in shaping the behavior of polar jets. Protostars, especially those of higher mass, emit intense radiation as they grow. This radiation interacts with the surrounding gas and dust, creating a complex feedback loop with the jets. In some cases, the radiation can ionize the material in the jets, making them even more visible in specific wavelengths, such as ultraviolet or X-rays. In other scenarios, the radiation can suppress jet formation, particularly in regions of high stellar density where multiple protostars compete for dominance. Understanding this interplay is crucial for deciphering the life cycle of stars in various environments, from isolated regions of a galaxy to densely packed star-forming clusters. The discovery of episodic jets adds another layer of intrigue to this topic. Unlike continuous outflows, episodic jets are emitted in bursts, with intervals of relative calm between eruptions. These bursts often leave behind a series of knots, or bullets, of ejected material, which can be traced back to changes in the accretion process around the protostar. Episodic jets provide a unique opportunity to study the timeline of a star's growth, as each knot represents a snapshot of its developmental history. Observing these features requires precise timing and advanced instruments, but the rewards are immense, offering a dynamic view of star formation that goes beyond static images. Polar jets also serve as a natural laboratory for studying the behavior of magnetic fields. The interaction between the jets and the magnetic fields in their environment is a subject of intense research. These fields not only guide the flow of material but also influence the temperature, density, and velocity of the jets. By mapping the magnetic fields in regions with active jets, astronomers can gain insights into their structure and strength, as well as their role in the broader dynamics of the molecular cloud. This research has implications for understanding the role of magnetic fields in other cosmic phenomena, such as the formation of planetary systems and the dynamics of galactic disks. The impact of polar jets on the surrounding interstellar medium extends beyond their immediate vicinity. As the jets interact with the molecular cloud, they create expanding shells of material that can trigger the formation of new stars in adjacent regions. This phenomenon, known as triggered star formation, highlights the interconnected nature of stellar nurseries, where the birth of one star can set off a chain reaction, leading to the creation of an entire cluster. These cascading effects underscore the importance of jets as agents of change, capable of shaping the destiny of entire regions of a galaxy. Polar jets are also a key factor in determining the final mass of a protostar. As material from the accretion disk is ejected through the jets, the protostar loses a portion of its potential growth. This process, known as mass loss, is essential for regulating the size of the star and preventing runaway accretion. Without this mechanism, many protostars would grow to unsustainable sizes, disrupting the balance of their systems. By expelling excess material, the jets ensure that the star reaches a stable configuration, setting the stage for its evolution into a main sequence star. In recent years, advances in technology have revolutionized our ability to study polar jets. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have provided unprecedented views of these phenomena, capturing their intricate details with remarkable clarity. For example, ALMA's ability to observe cold gas and dust at high resolution has revealed the fine structure of jets and their interaction with the surrounding medium. Meanwhile, Hubble's imaging capabilities have highlighted the stunning visual beauty of jets, showcasing their luminous trails against the backdrop of the cosmos. The potential for future discoveries is immense, particularly as new observatories like the James Webb Space Telescope, JWST, come online. With its ability to observe in the infrared, JWST is poised to reveal even more about the hidden processes driving jet formation and evolution. Scientists hope to use these observations to answer some of the most pressing questions about polar jets, such as the role of turbulence in shaping their structure and the precise mechanisms behind their collimation. Another frontier in the study of polar jets is their connection to planetary formation. As jets expel material from the accretion disk, they can influence the disk structure, creating gaps and rings that serve as the building blocks for planets. By studying these interactions, astronomers can gain insights into the early stages of planetary system development and the factors that determine the types and distribution of planets around a star. This research has profound implications for understanding the origins of our own solar system and the potential for life elsewhere in the universe. In a broader sense, polar jets challenge us to rethink our understanding of the cosmos. They are a reminder that the universe is not static but a dynamic and ever-changing tapestry of forces and interactions. Each jet, with its breathtaking speed and power, tells a story of creation and transformation, weaving together the threads of star formation, galactic evolution, and cosmic chemistry. These stories inspire us to look deeper, to question more, and to marvel at the complexity of the universe. The polar jets of protostars are more than just a scientific curiosity. They are a testament to the profound interconnectedness of the cosmos. They show us that even in the chaotic and violent process of star formation, there is order, beauty, and purpose. They remind us that the universe operates on scales both vast and minute, with each component playing a vital role in the grand cosmic dance. And they invite us to explore, to learn, and to imagine what lies beyond the horizon of our current understanding. As we continue to unravel the mysteries of polar jets, one of the most intriguing aspects is the way these jets can influence the chemical composition of their surroundings. When jets collide with the interstellar medium, they trigger a cascade of chemical reactions, forming complex molecules that could later seed the birth of planets and, potentially, life. These regions, often referred to as shock fronts, are laboratories of intense chemistry, where high-energy interactions break apart simple molecules like hydrogen and oxygen, only for them to recombine into more complex structures. The molecules formed in these shock fronts can include water, carbon monoxide, and even organic compounds like methanol. By studying these chemical traces, astronomers can map the history of a protostar's jets and gain insights into the conditions that led to their formation. The presence of water, in particular, is a tantalizing clue, as it raises questions about how much of this water might eventually make its way into planetary systems, possibly contributing to the development of habitable worlds. Another fascinating angle is how polar jets contribute to the redistribution of angular momentum in a star-forming system. In the early stages of star formation, the collapse of a molecular cloud generates enormous amounts of angular momentum, which, if unchecked, could prevent the star from forming. Jets act as a release valve, carrying away excess angular momentum and allowing the protostar to continue its growth. This delicate balancing act is a critical step in the life cycle of a star and demonstrates the intricate interplay of forces at work in the cosmos. The interaction of jets with their environment also sheds light on the broader structure of star-forming regions. For instance, observations have shown that jets can carve out cavities in the surrounding molecular clouds, creating tunnels through which light from the protostar can escape. These cavities, often illuminated by the light of the young star, create stunning visual displays that reveal the complex geometry of these regions. They also provide astronomers with a clear view of the protostar itself, which is often obscured by thick clouds of gas and dust. On a larger scale, polar jets contribute to the enrichment of the interstellar medium with heavy elements. As jets propagate through space, they carry with them material that has been processed in the high-energy environment near the protostar. This material, when it eventually mixes with the surrounding gas, contributes to the chemical diversity of the galaxy. Over time, this enrichment process plays a key role in the evolution of galaxies, enabling the formation of new stars and planets with a broader range of chemical compositions. The dynamics of polar jets also provide clues about the behavior of magnetic fields on cosmic scales. By analyzing the polarization of light emitted by jets, astronomers can infer the orientation and strength of magnetic fields in these regions. These observations not only enhance our understanding of the jets themselves but also offer a window into the role of magnetic fields in shaping the structure and evolution of galaxies. The insights gained from studying protostellar jets can therefore inform our understanding of phenomena as diverse as the formation of spiral arms in galaxies and the collimation of relativistic jets in quasars. Episodic variability in jets, which we touched on earlier, raises profound questions about the nature of accretion processes in protostars. What causes a protostar to alternate between periods of intense jet activity and relative quiet? Some researchers suggest that these cycles may be linked to instabilities in the accretion disk, where fluctuations in density and temperature lead to bursts of material falling onto the protostar. Others point to interactions with companion stars or planets as potential triggers for episodic behavior. Resolving these questions will require not only detailed observations but also sophisticated simulations that can capture the complex interplay of forces at work. Simulations have already proven invaluable in advancing our understanding of polar jets. By creating detailed models of jet formation and evolution, scientists can test their theories against observational data and refine their understanding of the underlying physics. These simulations have revealed, for example, how small variations in the initial conditions of a molecular cloud can lead to vastly different outcomes in jet structure and behavior. They also highlight the importance of feedback processes, where the jets themselves influence the environment in ways that alter their own evolution. The role of polar jets in planetary system formation is another area ripe for exploration. As jets sculpt the accretion disk, they create regions of varying density and temperature that can influence the aggregation of dust and gas into planetesimals, the building blocks of planets. In some cases, jets may even help to clear out debris, creating pathways that allow newly formed planets to migrate within the disk. By studying these interactions, astronomers hope to answer long-standing questions about the origins of planetary systems, including why some systems form gas giants close to their stars while others produce terrestrial planets in stable, distant orbits. The potential for future discoveries in this field is immense, especially as new technologies come online. Instruments like the Extremely Large Telescope, ELT, and space missions like the European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, promise to deliver unprecedented views of protostellar systems and their jets. With their ability to capture high-resolution spectra, these tools will enable scientists to probe the composition, velocity, and temperature of jets with unparalleled precision. They will also allow researchers to study jets in distant galaxies, providing a broader context for understanding these phenomena. The study of polar jets is not just about understanding the mechanics of star formation. It's about uncovering the story of how the universe builds itself, one star and planet at a time. Each discovery adds a new piece to the puzzle, revealing a cosmos that is as dynamic as it is beautiful. The intricate dance of forces that gives rise to jets, from the interplay of gravity and magnetism to the flow of matter and energy, is a testament to the complexity and elegance of the natural world. In many ways, polar jets challenge us to look beyond our immediate surroundings and consider the broader tapestry of existence. They remind us that the universe is a place of constant creation and transformation, where even the most violent processes serve a purpose in the grand scheme of things. They inspire us to keep asking questions, to keep pushing the boundaries of what we know, and to marvel at the endless possibilities that lie ahead. The deeper we delve into the enigma of polar jets, the more we begin to appreciate their role as cosmic sculptors. These streams of plasma don't just emerge and vanish, they leave lasting imprints on the structure of the universe. For example, the cavities carved out by jets in molecular clouds serve as evidence of their passage long after the protostar has matured into a full-fledged star. These cavities, often hundreds of light-years in diameter, reveal the immense scale of the forces at play, reshaping the landscape of star-forming regions and creating space for future generations of stars to emerge. One particularly compelling aspect of polar jets is their impact on neighboring stars and protostars. Star-forming regions often contain multiple nascent stars in close proximity. When a jet from one protostar intersects the environment of another, it can trigger a cascade of interactions that influence the latter's development. These interactions can either accelerate or hinder the star formation process, depending on the angle, velocity, and density of the jet. By studying these cases, astronomers gain valuable insights into the interconnected nature of stellar nurseries. A closer look at these interactions also reveals the role of feedback loops in regulating star formation. Jets act as both creators and destroyers, pushing material away from the protostar while simultaneously compressing surrounding gas, triggering the collapse of new regions. This dual role makes them one of the most fascinating aspects of stellar evolution. They are not merely byproducts of star formation, they are active participants in shaping the galaxy's future. Observations of jets also challenge our understanding of time scales and cosmic events. For instance, the velocity of material ejected by jets can range from hundreds to thousands of kilometers per second. These speeds mean that some jets can stretch across light years in mere millennia, a blink of an eye in astronomical terms. Yet the processes that produce these jets, including the accretion of material onto the protostar, can span millions of years. This disparity between the rapid motion of jets and the slow evolution of their sources highlights the complex interplay between short-term dynamics and long-term development in the cosmos. One fascinating aspect of jet studies is the way astronomers use them as cosmic clocks. By measuring the distance between a jet source and its current position, and knowing its velocity, scientists can estimate when the jet was launched. This provides a timeline of the protostar's activity and offers clues about the environment's evolution during that time. When combined with other data, such as the age of the surrounding molecular cloud, these timelines help reconstruct the history of star-forming regions, painting a picture of their development over millions of years. Another area of active research involves the interaction of jets with interstellar magnetic fields. These magnetic fields, often invisible to traditional observational methods, can be mapped indirectly by studying how jets twist and align as they propagate. Such studies reveal that magnetic fields play a crucial role in shaping not just individual jets, but also the larger structures of galaxies. Understanding these interactions provides a link between the small-scale phenomena of star formation and the large-scale architecture of the universe. The discovery of collimated jets in unexpected places, such as brown dwarfs and young stellar objects outside traditional star-forming regions, has further expanded the scope of this field. Brown dwarfs, often described as failed stars, because they lack the mass to sustain nuclear fusion, were not initially expected to produce jets. Yet observations have revealed that they, too, can launch powerful streams of material. This raises questions about the universality of jet formation mechanisms and suggests that the conditions for producing jets might be more common than previously thought. Advancements in computational modeling have also shed light on the turbulent processes occurring within the accretion disks that give rise to jets. These disks are far from uniform. They are dynamic, chaotic environments where instabilities and shock waves create pockets of intense activity. Simulations have shown how these localized events can produce the bursts of energy needed to launch jets, linking the microphysics of disk turbulence to the macrostructures observed in jets. One particularly intriguing discovery is the role of companion objects in shaping jets. Binary systems, where two stars orbit a common center of mass, often produce jets that are markedly different from those of single-star systems. The gravitational influence of the companion star can create complex patterns in the jet structure, including spirals and knots. Observing these patterns allows astronomers to infer the presence of companion stars that might otherwise remain hidden, adding another layer of complexity to the study of protostellar systems. The diversity of jet phenomena is a testament to the creativity of nature in solving the challenges of star formation. Every jet tells a story, not just of the star it emerged from but of the environment it traverses and the cosmic forces it interacts with. This makes the study of jets a multidisciplinary endeavor, requiring expertise in astrophysics, chemistry, and even fluid dynamics. As we look ahead, the future of jet research seems boundless. New technologies, such as adaptive optics and machine learning algorithms for data analysis, promise to accelerate discoveries and deepen our understanding. Instruments like the James Webb Space Telescope, with its unparalleled sensitivity to infrared light, are already transforming our view of protostellar regions, revealing details that were previously hidden. These advancements will undoubtedly refine our models and challenge our assumptions, driving the field forward in exciting new directions. At its core, the study of polar jets is a reminder of the interconnectedness of the cosmos. These seemingly isolated streams of plasma are part of a vast network of processes that shape galaxies, create stars, and lay the groundwork for planetary systems. They are both a product of their environment and a force that reshapes it, exemplifying the dynamic balance that governs the universe. As we continue to explore this phenomenon, one thing becomes clear: the story of polar jets is far from over. Each new discovery opens up fresh questions, inviting us to look deeper and think more broadly about the forces that shape our universe. In doing so, we not only expand our knowledge but also our sense of wonder, reminding us why we look to the stars in the first place. The ongoing exploration of polar jets from protostars invites us to ponder the profound interconnectedness of the cosmos. These phenomena represent more than just isolated bursts of energy. They symbolize the intricate dance of matter and energy that defines the universe. The story of polar jets is not one of randomness, but of precise mechanisms working together to forge new stars and sculpt the interstellar medium. The significance of polar jets extends to the formation of planetary systems. When jets expel excess angular momentum, they enable the surrounding accretion disk to remain stable, giving it the time and space needed to coalesce into planets, moons, and other celestial bodies. Without this balancing act, the raw materials for planets might simply spiral into the protostar or disperse into the surrounding environment. Thus, polar jets may play an indirect but crucial role in shaping the environments where life can eventually arise. Further research has shown that the chemical composition of jets provides valuable insights into the conditions of the regions they emerge from. Spectroscopic studies of jets often reveal the presence of complex molecules, such as water, carbon monoxide, and even organic compounds. These findings suggest that jets could act as chemical factories, distributing these essential building blocks of life across the cosmos. When these jets interact with molecular clouds, they may seed distant regions with the ingredients necessary for star formation and potentially life itself. One of the most captivating aspects of polar jets is their role as natural particle accelerators. Observations have revealed that some jets propel charged particles to near light speeds, generating intense radiation detectable across vast distances. This high-energy activity offers a window into physical processes that cannot be replicated in Earth-based laboratories. By studying these jets, scientists gain insights into the fundamental laws of physics, including the behavior of plasma and the interaction of matter with intense magnetic fields. Jets also illuminate the broader context of galaxy evolution. In massive star-forming regions, where countless protostars are simultaneously generating jets, the combined effect can shape entire star clusters and influence the dynamics of the host galaxy. Over millions of years, these jets contribute to the recycling of matter, dispersing heavy elements forged in earlier generations of stars and enriching the interstellar medium. This cyclical process ensures that each generation of stars benefits from the chemical legacy of its predecessors, highlighting the long-term impact of these seemingly transient phenomena. Technological advancements continue to push the boundaries of what we can learn about polar jets. Instruments like the Very Large Array, VLA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, allow astronomers to study jets at unprecedented resolutions, revealing structures and dynamics that were previously invisible. High-energy observatories, such as the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope, complement these efforts by detecting the radiation emitted by the fastest-moving particles within jets. Collaboration across disciplines has also been pivotal. Astrophysicists work alongside computational scientists to simulate jet formation and evolution, while chemists analyze the molecular signatures within jets to decode their chemical histories. This multidisciplinary approach ensures that no detail is overlooked, creating a holistic understanding of these extraordinary phenomena. Polar jets are not limited to protostars. They have analogues in other astrophysical contexts, such as black holes and neutron stars, where similar processes of accretion and angular momentum transfer produce collimated outflows. Comparing jets from these vastly different systems provides valuable insights into universal principles governing the behavior of matter and energy under extreme conditions. The educational value of polar jets is equally compelling. Their striking visuals and dynamic nature make them ideal subjects for inspiring the next generation of scientists. Many outreach programs and documentaries feature images and simulations of jets, sparking curiosity about the cosmos and encouraging young minds to explore careers in science and technology. One of the most enduring mysteries of polar jets is their remarkable stability over vast distances. Despite traveling through turbulent and chaotic environments, these jets maintain their collimation, often extending for dozens or even hundreds of light years. Understanding the mechanisms behind this stability is a major focus of current research, with implications for fields ranging from plasma physics to space exploration. The study of jets also forces us to confront the limitations of our current understanding. While we have made significant progress in deciphering their origins and behavior, many questions remain unanswered. For instance, the exact mechanism by which magnetic fields channel and accelerate material remains a topic of debate. Similarly, the role of turbulence within the accretion disk and its influence on jet formation continues to challenge theoretical models. As we refine our tools and expand our observational capabilities, we are likely to uncover new layers of complexity in polar jets. These discoveries will not only deepen our understanding of star formation but also shed light on broader cosmic phenomena, such as the formation of galaxies and the distribution of matter in the universe. Polar jets remind us that the cosmos is a place of constant motion and transformation. They embody the dynamic processes that shape stars, planets, and galaxies, offering a glimpse into the forces that govern the universe. Their study is not just an exploration of the stars but a journey into the very essence of existence. The story of polar jets is a testament to the power of curiosity and the human spirit of exploration. Each new discovery brings us closer to understanding our place in the cosmos, revealing a universe that is as intricate as it is awe-inspiring. As we continue to unlock the secrets of polar jets, we are reminded that the journey of discovery is as infinite as the stars themselves. The journey into the mysteries of polar jets takes us deeper into the heart of how the universe orchestrates its celestial mechanics. These powerful outflows, spanning from protostars to supermassive black holes, act as cosmic messengers, carrying information about the environments they originate from. Their intricate structures, precise collimation, and breathtaking scales reflect a delicate balance of forces, a dynamic interplay between gravity, magnetism, and energy release. One of the more captivating aspects of polar jets is their ability to sculpt their surroundings. As jets emerge from a protostar's accretion disk, they interact with the interstellar medium, carving out cavities and creating bow shocks where the fast-moving jet material collides with slower-moving gas. These interactions leave behind signatures that astronomers can observe, such as Helical objects, luminous patches of gas excited by the jets. Each Helical object tells a story about the velocity, density, and composition of both the jet and the medium it encounters. The formation of these jets involves the conversion of gravitational energy into kinetic and magnetic energy. When material from the accretion disk spirals inward, it heats up and emits intense radiation, creating pressure gradients. These gradients, combined with the twisting magnetic fields, launch material outward in two opposite directions, forming the bipolar jets. However, the precise details of how these mechanisms function remain an area of active investigation. Current simulations strive to replicate these conditions, offering glimpses into processes too distant or obscure to observe directly. Jets are not static phenomena. They evolve over time as the protostar grows and the accretion disk changes. Early in the protostar's life, jets may be erratic, with bursts of energy corresponding to fluctuating accretion rates. As the system stabilizes, the jets become more collimated and sustained, extending farther into space. Eventually, as the accretion process winds down and the protostar transitions into a mature star, the jets dissipate, leaving behind an enriched and structured interstellar medium. The influence of polar jets extends beyond the immediate vicinity of the protostar. By injecting energy and momentum into the surrounding medium, jets can trigger new episodes of star formation. In regions of high star-forming activity, such as stellar nurseries, the combined effects of multiple jets can compress gas clouds, causing them to collapse under their own gravity and form new protostars. This cascading effect demonstrates the interconnectedness of cosmic phenomena, where the birth of one star can set the stage for the formation of others. In addition to their role in star formation, polar jets provide a unique laboratory for studying fundamental physics. The extreme conditions within jets, such as high velocities, strong magnetic fields, and relativistic particle acceleration, mirror environments found near black holes, neutron stars, and active galactic nuclei. By comparing jets across these different contexts, researchers can test theories about the behavior of plasma, the generation of magnetic fields, and the conversion of energy into motion. Another fascinating aspect of polar jets is their ability to serve as natural markers of a protostar's rotation axis. Since jets are aligned with the magnetic field lines of the accretion disk, their orientation provides clues about the angular momentum and spin of the forming star. These details are crucial for understanding how stars inherit and distribute angular momentum, a key factor in the formation of planetary systems. For example, the alignment or misalignment of a planet's orbit with its star's rotation axis may trace back to the dynamics of the protostar's jets. The study of jets also sheds light on the chemical evolution of the universe. As jets interact with the interstellar medium, they promote the formation of complex molecules by compressing and heating the gas. Some of these molecules, such as water and carbon-based compounds, are essential for life as we know it. The discovery of these compounds within jets raises intriguing questions about their potential to seed distant regions of space with the raw materials for life. The observational techniques used to study jets are continually advancing, driven by the need to capture more detail and resolve finer structures. Radio telescopes, such as ALMA, excel at probing the cold, dense regions where jets originate, while optical and infrared observatories, like the Hubble Space Telescope and the James Webb Space Telescope, reveal the jet's interactions with their surroundings. High-energy instruments, including X-ray and gamma-ray observatories, detect the energetic processes occurring within the jets themselves. Despite these advancements, challenges remain. Jets are often obscured by the dense clouds of gas and dust that surround their parent protostars, making it difficult to observe their origins directly. Additionally, the sheer scale and variability of jets require long-term monitoring to capture their full life cycle. Addressing these challenges will require innovative approaches, such as combining data from multiple wavelengths and employing machine learning to analyze large datasets. The study of polar jets is not just an academic pursuit, it has practical implications for understanding the broader universe. By unraveling the mechanisms behind jet formation and behavior, scientists gain insights into the processes that govern the formation of stars, galaxies, and planetary systems. These insights, in turn, inform models of cosmic evolution, helping to answer fundamental questions about the origins of the universe and our place within it. Ultimately, polar jets remind us of the beauty and complexity of the cosmos. They are a testament to the power of nature to create order from chaos, transforming swirling disks of gas and dust into structured, luminous phenomena. As we continue to explore these cosmic outflows, we are not only uncovering the secrets of star formation but also deepening our appreciation for the intricate workings of the universe. Polar jets also provide a remarkable connection between the smallest scales of star formation and the largest structures in the universe. By studying these jets, we gain insight into a process that spans scales ranging from individual protostars to massive galactic environments. This connection highlights how seemingly local phenomena can influence the broader cosmos in unexpected ways. One particularly intriguing feature of polar jets is their apparent universality. Similar mechanisms that drive protostellar jets are observed in vastly different systems, such as quasars and pulsars. This commonality suggests that the physics behind these phenomena, particularly the interplay between magnetic fields and accretion processes, are fundamental to the way the universe organizes itself. Understanding polar jets at the protostar level may unlock broader insights into the nature of energy transfer and material ejection throughout the cosmos. Another key aspect of polar jets is their potential role in regulating the growth of stars. Without jets to expel excess angular momentum and energy, a protostar might accumulate material too rapidly, destabilizing the accretion disk or causing the star to grow beyond a sustainable size. Jets serve as a kind of cosmic safety valve, ensuring that the star-forming process remains balanced and sustainable. This regulatory role emphasizes the precision and efficiency inherent in nature's design. The study of polar jets has also inspired technological innovation. Instruments designed to capture high-resolution images of jets, such as adaptive optics systems and interferometry techniques, have led to breakthroughs in imaging technology that extend beyond astronomy. These advancements have applications in fields like medical imaging, communications, and even defense systems. In this way, the quest to understand polar jets has ripple effects that benefit humanity in unexpected ways. One of the most visually striking aspects of polar jets is their collimated structure, narrow beams of material that remain coherent over astonishing distances. This collimation raises intriguing questions about the role of magnetic fields and the mechanisms that maintain their stability. Magnetic reconnection, a process where magnetic field lines break and reconnect, is thought to play a key role in shaping and accelerating the jets. This process is not only crucial for understanding jets but also has implications for space weather phenomena, such as solar flares and coronal mass ejections. Polar jets also serve as a reminder of the dynamic and transient nature of the universe. While they can persist for thousands or even millions of years, they are ultimately ephemeral phenomena, temporary markers of a star's formative stages. Observing these jets is like catching a glimpse of a fleeting moment in cosmic history, a reminder of the ongoing cycles of creation and transformation that define the universe. In recent years, simulations of jet formation and evolution have become increasingly sophisticated, offering a window into processes that are otherwise inaccessible. These simulations combine fluid dynamics, magnetic field interactions, and radiative transfer to recreate the conditions around protostars. By comparing these models with observational data, scientists can refine their understanding of the physical mechanisms at play. The results not only advance our knowledge of jets but also contribute to broader fields like computational astrophysics and plasma physics. Jets also raise fascinating questions about the role of turbulence in the cosmos. While the jets themselves appear well-ordered, the regions from which they emerge, the accretion disks, are often highly turbulent. Understanding how these chaotic environments produce such highly collimated outflows is a key challenge in astrophysics. Insights into this process may shed light on other turbulent systems, from planetary atmospheres to galactic dynamics. The influence of polar jets extends even to the chemical enrichment of the interstellar medium. By ejecting material at high velocities, jets mix elements forged in stellar interiors with the surrounding gas, seeding future star-forming regions with heavy elements. This process is essential for the cosmic cycle of matter, where elements are continually recycled to create new stars, planets, and potentially life. Observations of jets also provide critical constraints on models of star formation. For example, the presence of jets can help identify young stellar objects that are otherwise obscured by dense clouds of gas and dust. By tracing the jets back to their sources, astronomers can map out star-forming regions with unprecedented precision. These observations contribute to a more complete picture of how stars and planetary systems come into being. As we look to the future, the study of polar jets promises to remain a vibrant and rapidly evolving field. Upcoming observatories, such as the Square Kilometre Array, SKA, and next-generation space telescopes, will provide even more detailed views of jets and their environments. These advancements will likely reveal new features and behaviors, challenging existing theories and inspiring fresh lines of inquiry. Polar jets also have a role to play in the search for extraterrestrial life. The regions influenced by jets, where material is compressed, heated, and mixed, may create environments conducive to the formation of complex molecules. By studying these regions, scientists can better understand the conditions that lead to the emergence of life and identify potential targets for future exploration. Ultimately, the story of polar jets is one of interconnectedness. They link the microcosm of individual stars with the macrocosm of galaxies and the universe as a whole. They demonstrate how small-scale processes can have far-reaching effects, shaping the evolution of entire star systems and contributing to the cosmic tapestry of matter and energy. As we continue to study polar jets, we are reminded of the boundless complexity and beauty of the universe. Each new discovery adds another layer to our understanding, revealing a cosmos that is both intricate and awe-inspiring. The journey of discovery is far from over, and the secrets of polar jets are sure to inspire and challenge future generations of scientists and explorers. The significance of polar jets stretches beyond their immediate environment. They serve as natural laboratories for understanding the interplay between matter, energy, and magnetic forces. These jets are not isolated phenomena. They are key players in the cosmic narrative, influencing the very fabric of the regions in which they emerge. By studying polar jets, scientists can unravel the intricate dance of forces that govern the universe on scales both large and small. The link between polar jets and the broader star-forming process cannot be overstated. In the chaotic environment of a stellar nursery, jets act as a stabilizing force, countering the gravitational collapse that drives star formation. They provide an escape route for angular momentum, a critical component in the formation of a stable star. Without jets, the protostar might fail to achieve equilibrium, either collapsing further into a dense object like a black hole or fragmenting into multiple smaller bodies. Polar jets also serve as cosmic markers, indicating the presence of active star formation. By identifying and studying these jets, astronomers can pinpoint regions where new stars are being born, even in the densest and most obscured parts of molecular clouds. These observations are particularly important for understanding the life cycle of stars and the processes that lead to the formation of planetary systems. One of the most fascinating aspects of polar jets is their potential to accelerate particles to near-light speeds. This phenomenon, known as relativistic jet activity, is more commonly associated with massive black holes and neutron stars, but the underlying physics appears to have parallels in the protostellar environment. The study of particle acceleration in jets provides insights into fundamental processes like magnetic reconnection and shockwave interactions, which have implications for fields ranging from space weather to high-energy astrophysics. The material ejected by polar jets often travels vast distances, carrying with it a wealth of information about the conditions near the protostar. By analyzing the composition of this material, scientists can gain insights into the chemical processes occurring within the accretion disk. These observations contribute to our understanding of how the building blocks of planets, and potentially life, are distributed throughout the galaxy. Another intriguing feature of polar jets is their role in shaping the interstellar medium. As jets collide with surrounding gas and dust, they create shockwaves that compress and heat the material, triggering new waves of star formation. This cascading effect highlights the interconnected nature of the cosmos, where the birth of one star can influence the formation of countless others. This feedback mechanism is a key component of galactic evolution, illustrating how small-scale processes can have galaxy-wide consequences. In addition to their physical and chemical impact, polar jets also provide a unique opportunity to test and refine astrophysical theories. The detailed observations of jets made possible by modern telescopes have revealed features that challenge existing models, prompting the development of more sophisticated simulations and theoretical frameworks. These efforts not only advance our understanding of jets but also contribute to broader fields like plasma physics and magnetohydrodynamics. The study of polar jets has also led to unexpected connections with other areas of science. For example, the processes that drive jet formation share similarities with phenomena observed in laboratory plasma experiments, and even in industrial applications like nuclear fusion. By drawing parallels between these seemingly disparate fields, scientists can leverage insights from one domain to advance another, demonstrating the interdisciplinary nature of modern research. Looking deeper into the physics of polar jets, one cannot ignore the role of angular momentum. The conservation of angular momentum is a fundamental principle in physics, and polar jets provide a dramatic illustration of how this principle operates on a cosmic scale. As material spirals into the protostar, it gains rotational energy, which must be shed for the star to form successfully. Jets serve as the mechanism for this energy transfer, ejecting excess angular momentum into space and allowing the protostar to continue its evolution. The study of magnetic fields is central to understanding polar jets. Magnetic fields are thought to be the primary force shaping and accelerating the jets, acting as conduits for energy transfer from the accretion disk to the surrounding space. These fields are complex and dynamic, constantly interacting with the inflowing material and the broader interstellar environment. Observing and modeling these interactions is a major challenge in astrophysics, but it holds the key to unlocking many of the mysteries surrounding jets. Polar jets are also windows into the early stages of planetary system formation. The material ejected by jets often includes dust and gas that would otherwise accumulate in the protoplanetary disk. By studying the composition and behavior of this material, scientists can gain insights into the conditions that lead to planet formation. This research has profound implications for understanding the origins of our own solar system and the potential for life elsewhere in the universe. One of the most visually stunning aspects of polar jets is their interaction with the surrounding environment. As jets plow through the interstellar medium, they create intricate patterns of shock waves, bow shocks, and ionized regions. These features can be observed across a wide range of wavelengths, from radio to infrared to X-rays, each revealing a different aspect of the jet's impact. The resulting images are not only scientifically valuable but also a reminder of the sheer beauty and complexity of the universe. The scale of polar jets is another aspect that captures the imagination. These structures can stretch for light years, dwarfing the size of the protostar that generates them. Their longevity is equally impressive, with some jets persisting for thousands or even millions of years. This combination of scale and duration underscores the enduring influence of jets on their surroundings, shaping the evolution of their host systems over cosmic timescales. Advancements in technology have played a crucial role in the study of polar jets. High-resolution imaging techniques, such as those provided by the Atacama Large Millimeter/Submillimeter Array, ALMA, have allowed astronomers to observe jets in unprecedented detail. These observations have revealed fine structures and dynamics that were previously hidden, providing new insights into the processes driving jet formation and evolution. The future of polar jet research is bright, with new missions and instruments poised to take our understanding to the next level. Projects like the James Webb Space Telescope and next-generation ground-based observatories will provide even more detailed views of jets and their environments. These advancements promise to uncover new features and phenomena, deepening our appreciation of the complexity and beauty of polar jets. The prospect of future discoveries regarding polar jets is thrilling, especially as technology continues to bridge gaps in our knowledge. As telescopes and detectors grow more sensitive, scientists will be able to analyze fainter and more distant jets, unlocking the secrets of early star formation in regions previously inaccessible to observation. These advancements promise not only a deeper understanding of individual jets but also a broader perspective on how jets influence the formation and evolution of galaxies. One of the most tantalizing questions in polar jet research concerns their role in the chemical enrichment of the universe. As jets interact with the interstellar medium, they spread material ejected from the accretion disk, including elements formed in earlier generations of stars. This process contributes to the cosmic recycling of matter, seeding the galaxy with the ingredients necessary for planet formation and, potentially, life. Understanding the contribution of jets to this cycle is essential for piecing together the history of the universe. The study of jets also intersects with broader questions about the life cycle of stars. Jets are not exclusive to protostars. They are observed in other stages of stellar evolution, from young stars to dying stars shedding their outer layers. Comparing jets across these different contexts can provide insights into the universality of the mechanisms that produce them. Are the processes driving jets fundamentally the same across all these environments, or do they differ in ways that reflect the unique conditions of each stage? These questions lie at the forefront of astrophysical research. One particularly intriguing aspect of polar jets is their variability. Jets are not static. They exhibit fluctuations in brightness, velocity, and structure over time. These changes provide clues about the dynamic processes occurring in the accretion disk and the star itself. For example, variations in the jet's intensity may reflect changes in the rate of material flowing onto the protostar, offering a real-time glimpse into the star's growth and development. The relationship between jets and their host environment is also a rich area of study. Jets do not exist in isolation. They are part of a complex feedback loop involving the protostar, the accretion disk, and the surrounding molecular cloud. The energy and momentum carried by jets can shape the structure of the cloud, influencing the formation of other stars in the vicinity. This interplay highlights the interconnectedness of cosmic processes, where the actions of one star can ripple through its environment, leaving an imprint on the galaxy's evolution. The magnetic fields associated with polar jets are particularly fascinating. These fields are thought to play a dual role. They both launch the jets and collimating them into narrow beams. However, the exact mechanisms behind these processes remain a subject of debate. Observing the alignment and strength of magnetic fields in and around jets can shed light on this mystery, providing a deeper understanding of the fundamental forces shaping the universe. Polar jets also challenge our understanding of extreme conditions. The material within jets is subjected to immense pressures, temperatures, and velocities, creating an environment where familiar physical laws can take on surprising forms. For example, the high-energy particles in jets can generate radiation across a wide spectrum, from radio waves to X-rays. Studying this radiation allows scientists to probe conditions that cannot be replicated on Earth, offering a unique window into the physics of the cosmos. The role of shocks within jets is another area ripe for exploration. As jets collide with the interstellar medium, they generate shock waves that compress and heat the surrounding gas. These shocks can trigger chemical reactions, forming molecules that would not otherwise arise under such conditions. By studying the chemistry of these shocked regions, scientists can gain insights into the origins of complex organic molecules, which may have implications for the emergence of life. Polar jets also serve as cosmic accelerators, propelling particles to near-light speeds. This acceleration is driven by magnetic reconnection and shockwave interactions, processes that are poorly understood but have far-reaching implications. For instance, the particles accelerated by jets contribute to the cosmic ray population that permeates the galaxy. Understanding how jets accelerate particles can shed light on the origins of cosmic rays, a long-standing mystery in astrophysics. The interplay between jets and radiation is another fascinating topic. As jets emit high-energy particles, they interact with the radiation field of the protostar, creating complex feedback loops. This interaction can influence the jet's structure, velocity, and composition, adding another layer of complexity to an already intricate system. Observing these interactions requires multi-wavelength observations, combining data from radio, optical, infrared, and X-ray telescopes to create a comprehensive picture. On a larger scale, polar jets contribute to the regulation of star formation within galaxies. By injecting energy and momentum into the interstellar medium, jets can disrupt the conditions necessary for star formation, preventing the collapse of molecular clouds. This regulatory role, known as feedback, is crucial for understanding the balance between star formation and galactic evolution. Without this feedback, galaxies might experience runaway star formation, leading to vastly different structures and dynamics. The connection between jets and star clusters is another area of interest. Many protostars form in dense clusters, where the interactions between stars and their jets create a dynamic and chaotic environment. Studying these interactions can reveal how jets influence the distribution and motion of stars within clusters, providing insights into the early stages of cluster evolution. The future of polar jet research lies in the synergy between observations, simulations, and theory. Advanced computational models are allowing scientists to simulate the conditions within jets with unprecedented detail, providing a virtual laboratory for testing hypotheses. These simulations can be compared with observational data to refine our understanding and make predictions about jets in different environments. The ongoing exploration of polar jets is a testament to the power of human curiosity and ingenuity. These cosmic phenomena, born from the most fundamental processes of star formation, continue to challenge and inspire scientists, pushing the boundaries of what we know about the universe. As we delve deeper into the mysteries of jets, we are not only uncovering the secrets of the stars but also gaining a greater appreciation for the intricate and interconnected nature of the cosmos. As research into polar jets continues to expand, there's also an increasing focus on the technological advancements that will enable scientists to uncover more details. Upcoming space telescopes and ground-based observatories are set to revolutionize our understanding of jets. Instruments like the James Webb Space Telescope, JWST, and the Atacama Large Millimeter Array, ALMA, are already providing unprecedented views of young stellar objects and their polar jets. These observatories, with their high resolution and sensitivity, will allow scientists to study the fine details of jets, including their composition, velocity, and magnetic field structure. One of the key advances in technology will be the ability to observe jets across a broader range of wavelengths. For instance, while current telescopes can observe jets primarily in the optical, infrared, and radio spectra, future instruments will likely extend this to high-energy wavelengths like X-rays. The interaction of polar jets with their environments generates a wealth of high-energy phenomena, and capturing these emissions will provide a deeper understanding of the energetic processes involved. This will also allow scientists to better link the physical conditions in and around the jets with the larger-scale effects they have on their host environments. With more advanced data processing techniques, researchers are now able to detect and analyze weaker jets from stars that are much farther away, or in regions previously obscured by dust and gas. By looking at jets in star-forming regions at varying distances from Earth, scientists can begin to piece together how these phenomena operate across a range of environments. This could help answer questions about the universality of jet formation and whether the mechanisms driving them are similar in different regions of space. Another significant area of progress involves the study of jet precession, a phenomenon where the direction of the jet shifts over time. This can occur because of the dynamics in the accretion disk or due to gravitational interactions with nearby stars or other massive objects. Observing precession can give astronomers insight into the complex forces that influence the orientation of the jet and reveal information about the structure of the accretion disk. More data will help scientists understand how common precession is among protostars and how it affects the way jets interact with the surrounding gas. In addition to their role in star formation, polar jets are also believed to influence the evolution of planetary systems. Jets can eject large quantities of material from the accretion disk, potentially removing or redistributing the building blocks for planet formation. However, they can also provide the necessary energy to drive the chemical processes that create complex molecules, including some that are vital for life. Understanding how jets contribute to the distribution of these molecules will be crucial in our search for habitable worlds beyond our own solar system. One aspect of jet formation that remains puzzling is how the material within them can travel so fast. Jets often move at speeds approaching 10% of the speed of light, a velocity that seems almost impossible considering the relatively slow movement of material in the accretion disk. Researchers are investigating the role of magnetic fields and shockwaves in accelerating the particles to such extreme velocities. Theories suggest that magnetic reconnection and the interaction between the jet and its environment play a key role in this process, but the exact details are still unclear. Solving this puzzle will provide valuable insights into the physics of high-energy astrophysical phenomena. The role of polar jets in the broader context of galaxy evolution is another critical area of study. While jets are often seen as an individual characteristic of forming stars, they also play a role in the larger-scale processes that govern the structure and evolution of galaxies. As jets inject energy and momentum into the surrounding interstellar medium, they can regulate the rate of star formation, influence the distribution of gas and dust, and affect the development of galactic structures. By studying jets in the context of galaxy formation, scientists are beginning to realize that these phenomena are not just a byproduct of star formation, but rather a crucial part of the cosmic cycle. The discovery of jets from supermassive black holes in the centers of galaxies has further broadened our understanding of polar jets. These jets are not just seen in young stars but also in older systems, where they can span across vast distances, sometimes stretching beyond the boundaries of the galaxy. While these jets are vastly more powerful than those produced by young stars, they share many of the same underlying mechanisms. Comparing these large-scale jets with those emitted by newborn stars allows scientists to gain insights into the evolution of stars and galaxies, as well as the similarities between these different cosmic phenomena. On a more speculative note, polar jets may also have implications for life beyond Earth. While the notion of life existing in distant star systems is still firmly in the realm of science fiction, the discovery of complex organic molecules in the jets of protostars raises intriguing possibilities. The material ejected from these jets contains carbon, oxygen, and nitrogen, elements that form the basis of life as we know it. Could polar jets be playing a role in the formation of life-supporting compounds that could eventually lead to the emergence of life in other parts of the galaxy? As our understanding of chemistry and biology deepens, this question becomes increasingly relevant. The study of polar jets is still in its early stages, and many mysteries remain to be unraveled. For example, while we know that these jets are powered by the accretion of material onto a protostar, we do not yet fully understand the precise mechanisms that drive the acceleration of the material or the formation of the jet itself. Are jets purely the result of the gravitational forces acting on the accretion disk, or do magnetic fields and other forces play a more active role in jet formation? Current observations point to the importance of both, but a comprehensive theory remains elusive. Even more intriguing is the potential for polar jets to teach us about the origins of the universe itself. By studying how material behaves in the intense gravitational fields around newborn stars, we can gain insights into the fundamental physics that govern not just star formation, but also the very structure of spacetime. The role of magnetic fields, the dynamics of accretion disks, and the behavior of matter at extreme temperatures and pressures are all key to understanding how the universe works on its most fundamental level. As scientists continue to observe and model the behavior of these fascinating cosmic phenomena, it is likely that we will uncover new aspects of the formation and evolution of stars, galaxies, and even the universe as a whole. The mysteries of polar jets offer a glimpse into the complex, dynamic processes that govern the cosmos, and every new discovery takes us one step closer to understanding the forces that shape the stars, and the very fabric of space itself. Another fascinating area of research involving polar jets focuses on their interaction with the interstellar medium, ISM. The ISM, composed of gas, dust, and cosmic rays, acts as the building material for future stars and planets. Polar jets not only plow through this medium, but also inject energy, heat, and momentum into it. This interplay can lead to complex outcomes, from triggering the collapse of nearby gas clouds to disrupting the delicate balance necessary for star formation in certain regions. When jets collide with the ISM, they form structures known as Herbig-Haro (HH) objects. These glowing patches of ionized gas are the result of the high-velocity jets slamming into the surrounding material, creating shock waves that heat the gas to extreme temperatures. HH objects are incredibly valuable to astronomers because they act as signposts, marking the location of active star formation. By studying these objects, researchers can infer the properties of the jets, such as their velocity, temperature, and chemical composition, as well as the density and makeup of the ISM in that region. The influence of polar jets on the ISM is not limited to creating HH objects. Over time, the energy from these jets can shape the surrounding environment on a much larger scale. For example, jets can carve out cavities or bubbles in the dense clouds of gas and dust where stars are born. These structures can range in size from a few light years across to vast voids spanning tens or hundreds of light years. The presence of these cavities has profound implications for subsequent star formation in the region, as the redistribution of material can either foster or inhibit the creation of new stars. One key aspect of jet-ISM interaction is the feedback loop it creates. As jets deposit energy into the surrounding medium, they can generate turbulence, which, in turn, affects the stability of nearby gas clouds. In some cases, this turbulence may compress clouds, causing them to collapse under their own gravity and form new stars. In other cases, it may disperse the gas, preventing star formation. This dual role makes polar jets a central player in the regulation of star formation across the galaxy. Understanding the impact of polar jets on the ISM also has broader implications for galactic evolution. The process of star formation is not uniform. It occurs in bursts or waves, often triggered by external events such as supernova explosions, galactic collisions, or the activity of polar jets. By studying the ways in which jets influence their environments, scientists can better understand the larger-scale processes that drive the evolution of galaxies over billions of years. Interestingly, polar jets are not exclusive to low-mass protostars. They are also observed in massive stars, which form through similar processes but on much larger scales. Jets from massive stars are significantly more energetic and can influence their surroundings over greater distances. These jets often contribute to the formation of larger structures, such as giant molecular clouds or even stellar nurseries where new generations of stars are born. Comparing jets from low-mass and high-mass stars allows researchers to explore the commonalities and differences in the physics of jet formation, shedding light on the universality of these phenomena. A deeper understanding of polar jets also has implications for astrophysical modeling. Jets are a natural laboratory for studying magnetohydrodynamics, MHD, the field of physics that deals with the behavior of electrically conducting fluids like plasma in the presence of magnetic fields. MHD governs many processes in the universe, from the behavior of the sun's corona to the dynamics of entire galaxies. Polar jets, with their intricate interplay of magnetic fields, gravity, and high-energy particles, provide a unique opportunity to test and refine MHD theories. Moreover, the study of polar jets is increasingly interdisciplinary, drawing on advances in computational modeling, laboratory plasma experiments, and astronomical observations. Modern supercomputers allow scientists to simulate the formation and evolution of jets in incredible detail, capturing phenomena that were once impossible to study. These simulations not only help researchers interpret observational data but also predict what might be seen with future telescopes. Another compelling avenue of exploration involves the role of polar jets in cosmic recycling. The material ejected by jets, rich in heavy elements formed through nuclear fusion, eventually mixes back into the ISM. Over time, this material contributes to the enrichment of the galaxy, providing the raw ingredients for the next generation of stars and planets. This cycle of matter, driven in part by jets, is fundamental to the cosmic ecosystem. In addition to their scientific importance, polar jets hold a certain poetic appeal. They are among the most dynamic and visually stunning phenomena in the universe, with their intricate, glowing filaments stretching across light years of space. Images captured by telescopes like Hubble and ALMA reveal the beauty and complexity of these jets, inspiring wonder and curiosity about the forces that shape our cosmos. As we continue to explore these mysterious structures, new questions arise. For instance, could polar jets play a role in explaining some of the anomalies observed in star-forming regions? Are there variations in jet behavior that correlate with the properties of the host protostar or its environment? What can jets tell us about the conditions in the early universe, when the first stars and galaxies were forming? Each new observation brings us closer to answering these questions, but it also highlights how much remains unknown. The study of polar jets is a reminder of the vast complexity of the universe and our ongoing quest to unravel its mysteries. These jets are not just a byproduct of star formation, they are an integral part of the cosmic dance, shaping the evolution of stars, galaxies, and perhaps even life itself. The road ahead promises to be as exciting as it is challenging. With each new discovery, we deepen our understanding of these incredible phenomena, adding another piece to the puzzle of how the universe works. The mysteries of polar jets are far from solved, but they offer a window into the processes that have shaped the cosmos for billions of years, and will continue to do so for billions more. The influence of polar jets extends beyond their immediate environments, affecting neighboring systems and potentially altering the course of star formation in other regions of space. This domino effect emphasizes the interconnected nature of the cosmos, where no phenomenon exists in isolation. Jets are not just localized bursts of energy. They are threads in the vast tapestry of galactic evolution. Take, for example, the phenomenon of triggered star formation. As jets interact with the interstellar medium, they create shock waves that can compress nearby gas clouds. These shock fronts can act as catalysts for the collapse of these clouds, jump-starting the process of star formation. In this way, a single protostar's polar jets can indirectly lead to the birth of numerous stars in the surrounding region, amplifying their impact across light years of space. This cascading effect demonstrates the far-reaching influence of even the smallest celestial events on the grand scale of the universe. On the flip side, jets can also inhibit star formation. In some cases, the energy and turbulence introduced by the jets can disperse gas clouds, preventing them from coalescing into new stars. This dual nature, both fostering and stifling star formation, makes jets a critical factor in the balance of stellar nurseries. The intricate dance of creation and destruction driven by jets highlights the delicate equilibrium of the cosmos. Advances in technology have opened new windows into the study of these phenomena. High-resolution observations from cutting-edge telescopes, like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST, have revealed unprecedented details about the structure and dynamics of polar jets. These instruments allow astronomers to peer into the dense, dusty regions where stars are born, shedding light on the previously hidden early stages of star formation. One of the most striking discoveries has been the realization that jets are not always symmetrical. While many jets emerge as relatively straight, bipolar streams, others show signs of twisting, bending, or even breaking apart. These irregularities provide clues about the conditions in the protostar's immediate environment, such as the presence of nearby magnetic fields or gravitational influences from neighboring stars. Understanding these deviations helps researchers piece together the complex puzzle of jet formation and evolution. The study of jets also ties into the broader field of astrophysical outflows, which include phenomena like supernova explosions and galactic winds. By comparing jets to these other types of outflows, scientists can identify common mechanisms and underlying principles. For example, the role of magnetic fields in channeling and accelerating particles appears to be a recurring theme across many different scales of the universe, from protostars to entire galaxies. A particularly intriguing aspect of polar jets is their potential to serve as natural accelerators of cosmic rays. These high-energy particles, which travel through space at nearly the speed of light, are a major component of the universe's energetic landscape. Jets, with their powerful magnetic fields and intense energy, are thought to play a role in generating and accelerating these particles. If confirmed, this connection could provide valuable insights into one of the long-standing mysteries of astrophysics, the origin of cosmic rays. Looking forward, the future of jet research is bright, with several new missions and observatories poised to make significant contributions. Projects like the Square Kilometre Array, SKA, and next-generation space telescopes promise to deliver even more detailed observations, enabling researchers to study jets on previously inaccessible scales. These advancements will not only deepen our understanding of polar jets, but also provide a broader context for their role in the universe. Furthermore, the study of polar jets has implications for understanding our own origins. The Sun, like all stars, was once a protostar surrounded by an accretion disk. While the Sun's jets have long since dissipated, their legacy is imprinted on the solar system. The alignment of planetary orbits and the distribution of material in the early solar nebula were likely influenced by the Sun's jets. By studying jets in other systems, we can gain insights into the processes that shaped our cosmic neighborhood billions of years ago. Another exciting avenue of research involves the potential application of jet physics to other astrophysical phenomena. For instance, the mechanisms that drive polar jets and protostars may share similarities with those behind the relativistic jets observed in active galactic nuclei, AGN, or gamma-ray bursts. These connections suggest that the physics of jets operates on a continuum, spanning vastly different scales and energy levels. By bridging these gaps, scientists can build a more unified understanding of the universe's dynamic processes. Beyond their scientific significance, polar jets also inspire a sense of wonder and curiosity. They are a testament to the incredible forces at work in the universe, shaping and reshaping the cosmos in ways that are both beautiful and profound. Their study reminds us of the intricate complexity of the universe and our ongoing quest to understand it. As our knowledge of polar jets continues to expand, so too does our appreciation for the role they play in the grand narrative of the cosmos. They are not just a feature of star formation. They are a driving force in the evolution of galaxies, a bridge between the micro and the macro, and a key to unlocking some of the deepest mysteries of the universe. The journey to unravel their secrets is far from over, but each new discovery brings us closer to a more complete understanding of our cosmic origins and the forces that shape our place in the universe. The mysteries of polar jets extend into areas of theoretical physics and computational modeling, where researchers strive to simulate these phenomena with ever-increasing precision. Modern simulations incorporate complex interactions between magnetic fields, gravity, and matter, producing visualizations that closely mirror observations. These simulations are not just tools for validation, they also serve as laboratories for exploring scenarios that are impossible to recreate physically. For example, computational models can simulate the behavior of jets under varying conditions, such as changes in the accretion rate of the protostar or fluctuations in magnetic field strength. These experiments reveal how subtle variations can lead to dramatically different outcomes, from highly collimated jets to diffuse outflows. By testing these models against observed data, scientists refine their understanding of the principles governing jet formation and behavior. One of the most fascinating revelations from these studies is the role of magnetic reconnection in powering jets. Magnetic reconnection occurs when oppositely directed magnetic field lines break and reconnect, releasing vast amounts of energy. This process, familiar in phenomena like solar flares, is thought to play a critical role in the acceleration of particles within jets. Observing and modeling this mechanism in protostellar environments provides valuable insights into a universal process that operates across the cosmos. In addition to their theoretical importance, polar jets may hold practical implications for future space exploration. The study of jet mechanics could inform the development of propulsion technologies, such as those based on magnetohydrodynamics, MHD. While this idea remains speculative, understanding how nature accelerates particles to high speeds could inspire innovations in human-made systems. The interplay between jets and the interstellar medium also has implications for the search for life beyond Earth. Jets can alter the chemical composition of their surroundings by generating shock waves that trigger complex chemical reactions. These reactions may produce molecules essential for life, such as water and organic compounds. In regions where jets interact with dense clouds, the resulting chemical enrichment could create fertile environments for the emergence of life. Studying these processes helps us understand the conditions that may lead to habitable worlds elsewhere in the galaxy. Another avenue of research focuses on the life cycle of jets themselves. While jets are most prominent during the early stages of star formation, their influence can persist long after they fade. The remnants of jets, such as outflow cavities carved into the surrounding gas, can serve as records of their activity. By examining these structures, astronomers can reconstruct the history of star formation in a given region, offering a window into the past dynamics of stellar nurseries. Observations of jets in different evolutionary stages also reveal a continuum of activity, from the energetic outflows of young protostars to the more subdued emissions of older stars. This continuum underscores the idea that jets are not isolated events but rather integral components of a star's life cycle. Understanding this progression provides a more holistic view of stellar evolution and the interconnected processes that shape our galaxy. Polar jets also challenge our understanding of the laws of physics, particularly in the realm of high-energy phenomena. The extreme conditions within jets, marked by intense magnetic fields, rapid rotation, and relativistic particle speeds, test the limits of current theories. Observing and analyzing these conditions can help physicists refine models of magnetohydrodynamics and develop new frameworks for understanding energy transfer in astrophysical systems. The broader implications of polar jets extend to our understanding of galaxy formation and evolution. Jets from massive stars, particularly those in dense star-forming regions, can have a cumulative impact on the structure of their host galaxies. By injecting energy and momentum into the interstellar medium, these jets contribute to processes like galactic winds, which regulate the growth of galaxies by dispersing gas and suppressing star formation in certain regions. On the scale of galaxy clusters, similar processes occur with jets emitted by supermassive black holes at the centers of galaxies. While these jets operate on a much larger scale, their underlying physics shares similarities with those of protostellar jets. Studying polar jets and protostars can therefore provide insights into the behavior of jets in more extreme environments, offering a unified perspective on these seemingly disparate phenomena. As technology continues to advance, the future of polar jet research looks promising. Instruments capable of detecting faint emissions and resolving fine details will enable astronomers to study jets in greater depth and across a broader range of wavelengths. These observations will not only enhance our understanding of jets but also illuminate their connections to other astrophysical processes. The allure of polar jets lies not just in their scientific significance but also in their ability to inspire wonder. They remind us of the incredible power and complexity of the universe, as well as our capacity to unravel its mysteries. Through the study of jets, we gain a deeper appreciation for the forces that shape the cosmos and our place within it. Ultimately, the exploration of polar jets is a testament to humanity's enduring curiosity and ingenuity. As we continue to probe these enigmatic phenomena, we uncover not only the secrets of the stars but also the interconnectedness of all things in the universe. Each discovery brings us closer to answering some of the most profound questions about our origins and the nature of existence. Polar jets exemplify the interplay between order and chaos in the cosmos. These phenomena, while seemingly chaotic in their powerful ejections and twisting motions, follow precise physical principles dictated by the laws of nature. The structure of jets, their composition, and their dynamic evolution reflect the incredible complexity of the forces at work during the formation of stars. This juxtaposition of apparent randomness and underlying order is a recurring theme in astrophysics, one that drives our fascination with the universe. As astronomers delve deeper into the study of polar jets, they encounter new questions that challenge existing paradigms. For example, the exact mechanisms that determine the speed of jets remain an active area of research. While magnetic fields and accretion disks play key roles, variations in jet velocities suggest that additional factors may influence their dynamics. Understanding these nuances requires interdisciplinary approaches, combining observations, simulations, and theoretical models. Another area of exploration involves the relationship between polar jets and the eventual fate of their parent stars. Protostars evolve into main-sequence stars, but the characteristics of their early jets may leave lasting imprints. For instance, the orientation and intensity of jets can influence the rotation rates of stars, which in turn affects their magnetic activity and lifespan. Studying these connections helps astronomers trace the lineage of stars from their chaotic beginnings to their stable Middle Ages. In the context of stellar clusters, jets act as agents of both collaboration and competition. In dense clusters where many stars form simultaneously, jets can interact with one another, leading to complex patterns of motion and energy transfer. These interactions may even result in collisions between jets, producing unique signatures that astronomers can detect. The dynamics of such interactions shed light on the communal aspects of star formation, where individual stars contribute to the larger ecosystem of the cluster. The chemical enrichment caused by jets also has far-reaching consequences for the evolution of galaxies. As jets inject newly synthesized elements into the surrounding medium, they enrich the galactic environment with materials necessary for the formation of planets and, potentially, life. The distribution of these elements provides clues about the history of star formation in different regions of the galaxy, helping researchers reconstruct its evolutionary timeline. Interestingly, polar jets may also influence the habitability of planets forming within the same system. Jets can shape protoplanetary disks by carving out gaps, redistributing material, and altering the temperature profile. These changes can affect the types of planets that form and their eventual orbits. For example, a jet might prevent a gas giant from migrating inward, preserving the stability of a habitable zone. By studying these effects, scientists gain insights into the conditions that make planetary systems conducive to life. The study of jets also intersects with the search for exoplanets. Observing the environments around protostars can reveal clues about the early stages of planet formation. Polar jets, with their ability to illuminate the surrounding material, serve as natural beacons, highlighting regions of interest. This connection between jets and exoplanet science underscores the interdisciplinary nature of modern astronomy, where discoveries in one field often inform progress in another. From a philosophical perspective, polar jets remind us of the scale and complexity of the universe. They are a testament to the transformative power of natural forces, capable of sculpting matter and energy into structures of immense beauty and significance. At the same time, they challenge our understanding of fundamental physics, pushing the boundaries of what we know about the interaction of forces in extreme environments. Jets also serve as metaphors for the cyclical nature of the cosmos. They emerge from the collapse of gas and dust, heralding the birth of a new star, and in turn, they shape the material that will give rise to future generations of stars and planets. This cycle of creation and influence illustrates the interconnectedness of cosmic phenomena, where every event is both a product of its past and a precursor to its future. Looking to the future, the study of polar jets will continue to benefit from technological advancements and international collaborations. Space-based observatories, ground-based telescopes, and theoretical modeling will work in concert to uncover new details about these fascinating phenomena. These efforts will not only enhance our understanding of star formation but also provide broader insights into the processes that govern the universe. As we reflect on the significance of polar jets, we are reminded of the enduring human quest for knowledge. These celestial phenomena, millions of light years away, connect us to the cosmos in profound ways. Through the study of jets, we not only learn about the stars but also about ourselves, our curiosity, our ingenuity, and our place in the vast expanse of the universe. The mysteries of polar jets are far from fully understood, but each new discovery brings us closer to unraveling their secrets. They are windows into the fundamental processes of the cosmos, offering glimpses of the forces that shape galaxies, stars, and planets. In their dynamic motions and intricate structures, polar jets embody the wonder and complexity of the universe, inspiring generations of scientists and dreamers alike. The exploration of polar jets is not just an exercise in curiosity, it is a journey into understanding the very foundations of how stars, planets, and ultimately life come to be. These jets, often stretching for light years across the cosmos, tell a story of extraordinary energy and balance. They are nature's testament to the power of magnetic fields, gravity, and fluid dynamics working in harmony to sculpt the universe. Yet, in their intricate beauty, they also reveal the limitations of our knowledge, urging us to delve deeper into their mysteries. One of the enduring questions surrounding polar jets is their variability. Jets are not static. They pulsate, flicker, and even sometimes erupt in bursts of unexpected intensity. This variability may hold keys to understanding the inner workings of protostars themselves. What causes these fluctuations? Are they linked to sudden changes in the accretion rate of the disk or instabilities in the magnetic field? Observations of jets in real time, combined with simulations, have begun to shed light on these phenomena, but many aspects remain elusive. The role of polar jets in dispersing angular momentum is another area of active investigation. Angular momentum, a conserved quantity in physics, poses a paradox during star formation. As a collapsing cloud of gas condenses into a protostar, it should theoretically spin faster, much like an ice skater pulling in their arms. However, most stars do not end up spinning as rapidly as this process would suggest. Jets provide a solution to this problem by acting as channels for angular momentum to escape, allowing the protostar to stabilize. Understanding how this process unfolds is critical to modeling star formation accurately. Another intriguing aspect of jets is their apparent universality across different scales and environments. While protostellar jets are relatively small on the cosmic scale, jets from active galactic nuclei, AGN, associated with supermassive black holes operate on vastly larger scales, stretching across millions of light years. Despite their differences, both types of jets share common features, such as collimation, high velocities, and strong magnetic fields. Studying protostellar jets offers a microcosmic view of processes that govern much larger and more energetic systems, highlighting the interconnectedness of phenomena in the universe. Polar jets also serve as laboratories for studying high-energy physics. The particles within these jets are often accelerated to nearly the speed of light, providing conditions that are difficult to replicate on Earth. These relativistic speeds, combined with intense magnetic fields, create an environment where exotic physical processes can occur. For example, jets can produce synchrotron radiation, a type of electromagnetic emission generated when charged particles spiral along magnetic field lines. Observing this radiation gives astronomers clues about the composition and dynamics of jets. The interaction of jets with their surroundings is equally compelling. As jets plow through the interstellar medium, they create shock waves that compress and heat the gas, triggering complex chemical reactions. These reactions can lead to the formation of molecules like water, carbon monoxide, and even simple organic compounds. In this way, jets contribute to the chemical evolution of the galaxy, enriching it with the building blocks of life. This process is particularly significant in star-forming regions, where the interplay between jets and gas clouds can set the stage for the emergence of planetary systems. On a more speculative note, some researchers have considered the possibility that jets could influence the habitability of planets in nearby systems. By altering the density and distribution of material in protoplanetary disks, jets might affect the types of planets that form and their potential for hosting life. While this idea remains largely theoretical, it underscores the broader significance of jets in shaping not just stars but entire planetary systems. As observational technology advances, astronomers are beginning to detect jets in greater detail and at earlier stages of star formation. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have revolutionized our ability to study these phenomena by capturing high-resolution images of jets and their parent disks. These observations are complemented by data from space-based telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope, which can probe jets across multiple wavelengths. Together, these tools provide a more complete picture of the processes at work. Despite these advancements, many questions about polar jets remain unanswered. For instance, what determines the precise angle and direction of a jet? Why do some protostars produce more collimated jets than others? And how do jets evolve over time, from their initial bursts to their eventual dissipation? Addressing these questions will require not only better observations but also a deeper theoretical understanding of the physical principles that govern jet formation. The study of polar jets also has implications for our understanding of the universe's largest structures. Galactic jets, which are powered by supermassive black holes, share many characteristics with protostellar jets. By studying the smaller, more accessible jets of protostars, astronomers can gain insights into the mechanisms that drive their larger counterparts. This connection bridges the gap between the microcosm of star formation and the macrocosm of galaxy evolution, demonstrating the universality of physical laws. In a broader sense, polar jets remind us of the interconnectedness of all things in the universe. They illustrate how small-scale processes, like the collapse of a gas cloud, can have far-reaching effects, influencing the structure and composition of entire galaxies. At the same time, they highlight the intricate balance of forces that govern the cosmos, from the pull of gravity to the push of magnetic fields. As we continue to explore the mysteries of polar jets, we are not just learning about the stars, we are also expanding our understanding of the fundamental principles that shape the universe. Each new discovery brings us closer to answering age-old questions about our origins and our place in the cosmos. And in the process, we are reminded of the boundless curiosity that drives humanity to seek knowledge, even in the face of the vast unknown. The intricate dance of polar jets in star formation is a fascinating interplay of energy, matter, and physics. While these jets are dazzling displays of nature's mechanics, they also serve as a bridge connecting the intimate details of star birth to the grandeur of cosmic evolution. Yet, their mysteries only deepen as we peel back the layers of observation and theory. One critical area of investigation is the material composition of polar jets. The jets are primarily composed of ionized gas, or plasma, a state of matter where atoms are stripped of their electrons. This plasma is ejected at high velocities, creating a dynamic and chaotic environment. Embedded within this plasma are heavier elements, including metals such as iron and nickel, which are products of earlier generations of stars. The abundance and distribution of these elements within jets can offer valuable clues about the history of the interstellar medium from which the protostar emerged. Interestingly, the polar jets of protostars are also sources of molecular outflows, where cooler gas is pushed outward alongside the hotter ionized plasma. These molecular outflows are rich in complex compounds, including water, ammonia, and carbon monoxide. The chemistry of these molecules provides a snapshot of the early conditions in star-forming regions. By analyzing the spectra of these outflows, astronomers can trace the origins and pathways of various chemical reactions, offering insights into how the raw ingredients for planets and life are distributed throughout the galaxy. The interaction of jets with magnetic fields is another cornerstone of their behavior. Magnetic fields play a crucial role in launching and collimating jets, acting as both a guide and a restraint. These fields are thought to be generated by the rotation of the protostar and the accretion disk, creating a powerful dynamo effect. The geometry and strength of these fields determine how efficiently material is funneled into the jets and how narrowly they are focused. Yet, the magnetic fields themselves are enigmatic. Observing and measuring them directly is a formidable challenge, requiring sophisticated techniques such as polarimetry, which analyzes the orientation of light waves. Through these methods, astronomers can infer the alignment and intensity of magnetic fields in jets. Early results suggest that these fields are tightly wound, forming helical structures that spiral around the jet axis. These helical fields not only stabilize the jets but also accelerate particles to extreme speeds, creating the relativistic velocities observed in many systems. The high-energy processes occurring within polar jets also produce a range of electromagnetic emissions, spanning from radio waves to X-rays. Each wavelength reveals a different aspect of the jet's structure and dynamics. For instance, radio emissions often originate from synchrotron radiation, where electrons spiral along magnetic field lines. Meanwhile, X-rays may be produced in shock fronts, where fast-moving jets collide with slower material in the surrounding medium. By piecing together data from these emissions, astronomers can construct a multifaceted picture of jet behavior. Another layer of complexity lies in the role of feedback mechanisms. Jets are not isolated phenomena. They actively shape their surroundings, influencing the very regions they emerge from. As jets push through the interstellar medium, they create bow shocks, compressing gas and triggering bursts of star formation in nearby clouds. These processes contribute to the cyclical nature of stellar evolution, where the birth of one star can catalyze the formation of others. At the same time, jets can also disrupt their environments, clearing out gas and halting further star formation in certain regions. On a broader scale, polar jets contribute to the regulation of galactic ecosystems. By injecting energy and momentum into the interstellar medium, jets help maintain a delicate balance between star formation and gas dispersal. This balance is essential for the long-term sustainability of galaxies, preventing runaway star formation that could deplete gas reserves too quickly. In this way, jets act as cosmic gardeners, cultivating the conditions for new generations of stars and planets. One of the most tantalizing mysteries of polar jets is their longevity. Jets can persist for thousands to tens of thousands of years, far longer than the brief and chaotic phases of accretion that drive them. This persistence raises questions about the mechanisms that sustain jets over such extended periods. Are they continuously replenished by material from the disk, or do they operate in bursts, punctuated by periods of dormancy? Understanding this life cycle is key to unraveling the full story of jet evolution. The study of polar jets is also advancing rapidly thanks to technological innovations. Observatories like ALMA and the Very Large Array, VLA, have transformed our ability to study jets at sub-millimeter and radio wavelengths, revealing intricate details of their structure and composition. Meanwhile, space-based telescopes like the Chandra X-ray Observatory provide complementary views in high-energy regimes, capturing the most energetic phenomena in jets. These observations are further enriched by theoretical models and simulations, which allows scientists to test hypotheses and explore scenarios that are impossible to replicate in laboratories. One emerging area of research involves the connection between jets and disk fragmentation. In some cases, the accretion disk surrounding a protostar can become unstable, breaking into clumps that may eventually form companion stars or planets. Jets are thought to influence this fragmentation process by redistributing angular momentum and altering the density of material in the disk. By studying these interactions, astronomers hope to gain insights into the origins of binary star systems and the diversity of planetary architectures. Another fascinating avenue is the potential role of jets in the early stages of black hole formation. While polar jets are most commonly associated with protostars, they are also observed in other astrophysical contexts, including neutron stars and black holes. The underlying physics of jet formation appears to be remarkably consistent across these systems, suggesting a universal mechanism driven by accretion and magnetic fields. By drawing parallels between protostellar jets and their more extreme counterparts, scientists can deepen their understanding of high-energy astrophysics and the life cycles of massive stars. Ultimately, the study of polar jets is a testament to the interconnectedness of the cosmos. These jets, born from the humble collapse of gas clouds, link the microcosm of star formation to the macrocosm of galactic evolution. They are reminders of the profound balance and complexity that govern the universe, where even the most chaotic processes serve a greater purpose. As our tools and techniques continue to improve, the secrets of polar jets will undoubtedly yield new revelations, offering glimpses into the cosmic dance that shapes our universe. Polar jets also serve as windows into the extreme physical conditions of star-forming regions. The sheer velocity of these jets, often exceeding hundreds of kilometers per second, provides insight into the immense forces at play. These velocities are not arbitrary but stem from the intricate interplay of gravitational, magnetic, and thermal forces in the accretion process. The immense gravitational pull of the protostar accelerates material toward it, while magnetic fields redirect some of this material into jets. Thermal pressure from the intense heat near the accretion disk also contributes to this dynamic system. By studying the motion of these jets, scientists can indirectly measure the strength and configuration of these forces, creating a detailed picture of the physics at work in star formation. Additionally, the jets' interactions with their surroundings are not just destructive, they are also transformative. As jets plow through the interstellar medium, they create shock waves that compress and heat the gas in their path. These shocks can lead to the formation of dense clumps within the surrounding molecular clouds, which are the seeds for new stars. This process, known as triggered star formation, is a direct consequence of the feedback from polar jets. It illustrates how the birth of one star can set the stage for the birth of others, weaving a tapestry of stellar life across vast regions of space. However, this process is far from uniform. The impact of jets on the surrounding environment depends on several factors, including their speed, composition, and the density of the medium they encounter. In dense regions, jets can create dramatic bow shocks and carve out cavities in the gas. In less dense regions, the jets may disperse more freely, spreading their energy over larger volumes. This variability adds another layer of complexity to the study of jets, as researchers must consider a wide range of initial conditions and outcomes. One of the most visually striking features of polar jets is their collimation, their remarkable ability to maintain a narrow, beam-like structure over vast distances. This collimation is primarily attributed to the influence of magnetic fields, which act like a cosmic funnel, channeling material into focused streams. Without these fields, the jets would quickly disperse, losing their energy and coherence. The precise alignment and strength of these fields are critical to jet formation, and even slight variations can result in significantly different jet morphologies. Despite their focused nature, polar jets are not perfectly straight. Many jets exhibit kinks, knots, and wiggles along their length, suggesting that they are subject to instabilities and oscillations. These features are not random but reflect the dynamic processes occurring within the jets and their source regions. For instance, periodic variations in the accretion rate can create pulses of material that travel along the jet, appearing as knots in observational images. Similarly, interactions with surrounding gas can cause the jets to bend or deflect, adding to their complexity. The energy carried by polar jets is immense, but where does it all go? As jets travel outward, they eventually dissipate their energy into the surrounding medium. This dissipation occurs through a combination of processes, including shock heating, turbulence, and radiation. Shock heating occurs when the high-speed jets collide with slower-moving gas, converting kinetic energy into heat. This heat, in turn, causes the gas to emit radiation across various wavelengths, making the jets and their impact regions visible to telescopes. Turbulence is another key factor in energy dissipation. As jets interact with the interstellar medium, they stir the surrounding gas, creating chaotic motions that cascade down to smaller and smaller scales. This turbulent energy can remain in the gas for long periods, influencing its structure and dynamics. In some cases, turbulence may even prevent the gas from collapsing under its gravity, regulating the rate of star formation in the region. On a larger scale, polar jets contribute to the overall energy budget of galaxies. By injecting kinetic energy and momentum into the interstellar medium, jets help to maintain the dynamic equilibrium of galactic ecosystems. This equilibrium is essential for sustaining the conditions needed for star formation over billions of years. Without the influence of jets and other feedback mechanisms, galaxies could become either too quiescent, with all their gas locked into stars, or too turbulent, with no stable regions for star formation. The study of polar jets is also shedding light on the broader question of angular momentum transfer in star-forming systems. Angular momentum is a conserved quantity, and as gas falls toward a forming star, it must shed its excess angular momentum to allow further infall. Polar jets are thought to play a crucial role in this process by carrying away angular momentum from the system. This transfer allows the protostar to continue growing while maintaining a stable rotation rate. Understanding how angular momentum is redistributed is vital for explaining the observed properties of stars and planetary systems. As our observational capabilities improve, new discoveries about polar jets continue to emerge. High-resolution imaging from facilities like the Hubble Space Telescope and the James Webb Space Telescope has revealed intricate details of jet structure, while instruments like ALMA have provided unprecedented views of the cold molecular outflows associated with jets. These observations are complemented by theoretical models and simulations, which allow researchers to explore the underlying physics in controlled settings. Despite these advances, many questions about polar jets remain unanswered. For instance, what determines the lifetime of a jet? How do jets vary across different types of protostars? What role do jets play in the formation of binary and multiple star systems? These questions highlight the ongoing need for research and the potential for future breakthroughs. In the grand scheme of the cosmos, polar jets may seem like small-scale phenomena. Yet their impact reaches far beyond the confines of individual star-forming regions. By studying these jets, we gain insights into the processes that shape galaxies, regulate star formation, and even set the stage for the emergence of life. The mysteries of polar jets remind us of the interconnectedness of the universe, where the actions of a single star can ripple across vast cosmic distances. Polar jets also offer a unique perspective on the role of magnetic fields in cosmic phenomena. Magnetic fields are notoriously difficult to study because they are invisible and only indirectly observable through their effects. Yet, in the context of polar jets, these fields leave unmistakable fingerprints. The alignment of jets, their collimation, and even their rotational properties are all dictated by the magnetic environment of the protostar. By analyzing these characteristics, researchers can infer the strength and structure of magnetic fields in regions of space that are otherwise beyond our reach. The rotational properties of polar jets are particularly fascinating. Observations have shown that some jets exhibit a helical or corkscrew pattern, indicating that they carry angular momentum away from the protostar. This phenomenon, known as jet rotation, is a direct consequence of the star disk system's magnetic field lines. As material spirals inward through the accretion disk, it twists the magnetic field lines, which, in turn, transfer angular momentum outward via the jets. This intricate interplay between rotation, magnetic fields, and jet dynamics adds another layer of complexity to the study of star formation. Another critical aspect of polar jets is their chemical composition. Jets are not composed of pure hydrogen or helium, the most abundant elements in the universe. Instead, they carry a rich mixture of heavier elements and molecules, including carbon, oxygen, nitrogen, and even complex organic compounds. These materials are the byproducts of the accretion process and the extreme conditions near the protostar. As jets eject these elements into space, they contribute to the chemical enrichment of the interstellar medium, seeding future generations of stars and planets with the building blocks of life. The presence of complex organic molecules in jets has profound implications for astrobiology. These molecules, which include precursors to amino acids and other essential components of life, are thought to form in the warm, dense regions of the accretion disk. When ejected by the jets, they are dispersed into the surrounding molecular cloud, where they can become incorporated into new star systems. This process creates a direct link between star formation and the chemical conditions necessary for life, suggesting that the origins of life may be deeply rooted in the dynamics of polar jets. Furthermore, the influence of jets extends beyond the immediate vicinity of the protostar. Over time, the energy and momentum carried by jets can alter the large-scale structure of the parent molecular cloud. These effects are particularly evident in regions of intense star formation, where multiple jets from nearby protostars can create a network of shocks, outflows, and turbulence. This collective activity shapes the cloud's morphology, creating cavities, filaments, and other structures that are visible in observations across multiple wavelengths. Infrared and radio observations have been particularly instrumental in revealing the hidden world of polar jets. At these wavelengths, astronomers can peer through the dense dust and gas surrounding protostars, uncovering the intricate details of jet morphology and their interactions with the environment. High-resolution imaging has revealed that jets often consist of multiple components, including a fast-moving central core and slower-moving outer layers. This stratification provides clues about the physical conditions in the accretion disk and the mechanisms driving the jets. One of the most striking features of polar jets is their longevity. Despite being transient phenomena, jets can persist for thousands to tens of thousands of years, spanning a significant fraction of the protostar's early life. This extended duration allows jets to leave a lasting imprint on their surroundings, carving out channels in the molecular cloud and influencing the formation of subsequent generations of stars. The long lifetimes of jets also provide ample opportunities for astronomers to study them, making them invaluable laboratories for understanding the early stages of stellar evolution. In recent years, the study of polar jets has been revolutionized by advances in computational modeling. Simulations have become powerful tools for exploring the complex physics of jet formation and evolution. By recreating the conditions near a protostar, researchers can test hypotheses about the roles of magnetic fields, rotation, and accretion in jet dynamics. These models have successfully reproduced many observed features of jets, such as their collimation, knotty structures, and interactions with the interstellar medium. However, they have also revealed new puzzles, such as the exact mechanisms that regulate the energy and momentum of jets over time. One area of active research is the connection between polar jets and their parent star systems. Observations have shown that jets are not confined to single stars. They also occur in binary and multiple star systems. In these cases, the dynamics of jet formation become even more complex, as the gravitational interactions between the stars influence the accretion process and the orientation of the jets. Studying jets in these systems provides valuable insights into the diversity of star-forming environments and the role of gravitational interactions in shaping stellar evolution. The study of jets has also benefited from comparisons with similar phenomena in other astrophysical contexts. For instance, jets are not unique to protostars. They are also observed in systems ranging from young stellar objects to supermassive black holes. While the scales and energies of these jets differ, the underlying physical principles are remarkably similar. By comparing jets across these different contexts, astronomers can identify universal processes that operate across the cosmos, providing a unifying framework for understanding jet phenomena. As we continue to push the boundaries of observation and theory, the mysteries of polar jets remain a compelling frontier in astrophysics. These enigmatic structures, born from the chaos of star formation, offer a glimpse into the dynamic processes that shape our universe. They remind us that even the smallest scales of cosmic activity can have profound implications, influencing the evolution of galaxies, the chemistry of space, and the potential for life itself. The study of polar jets is not just a journey into the heart of star formation. It is a journey into the interconnected web of processes that define the cosmos. Polar jets also play a significant role in bridging the gap between theoretical astrophysics and observational science. While we can simulate and model many aspects of jet formation and behavior, it is the observations from advanced telescopes that provide the data necessary to validate or challenge these models. This interplay between theory and observation is crucial for advancing our understanding of the jet's physical mechanisms. By combining the predictive power of computational models with the precision of observational data, scientists are slowly piecing together the puzzle of how these jets operate on multiple scales. The interaction of jets with the surrounding environment offers a vivid demonstration of how energy and matter are transferred across vast distances in space. As jets plow through the interstellar medium, they generate shock waves that compress and heat the surrounding material. These shock waves can trigger the collapse of nearby gas clouds, potentially leading to the formation of new stars. In this way, polar jets act as both destroyers and creators, disrupting the existing structure of the molecular cloud while simultaneously seeding the birth of new stellar systems. One of the most intriguing aspects of polar jets is their episodic nature. Rather than being continuous streams of matter, jets are often observed as a series of discrete knots or blobs. These features suggest that the jets are launched in bursts, with periods of intense activity followed by relative quiescence. The reasons for this episodic behavior are not fully understood, but they are thought to be linked to the dynamics of the accretion disk. Variations in the rate of material falling onto the protostar could lead to fluctuations in the jet's intensity, creating the knotty structures observed in high-resolution images. These knots also provide a unique opportunity to study the properties of jets in greater detail. By measuring the velocities and compositions of individual knots, astronomers can gain insights into the conditions near the protostar at the time of their ejection. These measurements can reveal variations in temperature, density, and magnetic field strength, offering a time-lapse view of the processes occurring in the star disk system. This level of detail is crucial for understanding the complex interplay between accretion, magnetic fields, and jet dynamics. The discovery of polar jets has also had a profound impact on our understanding of the earliest stages of planetary system formation. The same accretion disks that give rise to jets are also the birthplaces of planets. As jets expel material from the system, they help clear out the disk, creating gaps and structures that are thought to influence the formation and migration of planets. By studying jets, scientists can gain insights into the conditions that shape the architectures of planetary systems, including our own solar system. The link between jets and planetary system formation is further underscored by the discovery of microjets in protoplanetary disks. These smaller-scale jets, observed in systems that are already forming planets, suggest that jet activity may persist well beyond the protostellar phase. Microjets are thought to arise from localized accretion events or interactions between the disk and magnetic fields. Their presence highlights the diverse manifestations of jet phenomena and their ongoing influence on the evolution of star systems. One of the most exciting frontiers in the study of polar jets is the use of multi-wavelength observations to probe their properties. Each wavelength band provides a different perspective on the jets, revealing features that are invisible at other wavelengths. For example, X-ray observations can detect the high-energy regions near the base of the jets, while infrared and radio observations can trace the cooler, denser material further out. By combining data from across the electromagnetic spectrum, astronomers can build a more complete picture of jet dynamics and their interactions with the environment. Advancements in telescope technology are also opening new windows into the study of jets. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST, are capable of resolving the fine details of jets and their surroundings with unprecedented clarity. These facilities allow scientists to study the physical and chemical processes occurring within jets at scales that were previously inaccessible. With each new observation, we move closer to understanding the full complexity of these extraordinary phenomena. Polar jets also serve as natural laboratories for studying extreme physics. The conditions near the base of the jets, where temperatures soar, densities peak, and magnetic fields dominate, are unlike anything we can replicate on Earth. These regions offer a unique opportunity to study processes such as magnetic reconnection, shock acceleration, and plasma instabilities. By understanding these processes in the context of jets, scientists can apply their findings to other astrophysical systems, from solar flares to black hole jets. The study of jets also has implications for understanding the broader universe. Jets are not confined to individual star systems. They play a role in shaping the large-scale structure of galaxies. In regions of intense star formation, the cumulative effect of many jets can create bubbles, cavities, and other features in the interstellar medium. These structures influence the distribution of gas and dust within the galaxy, affecting future generations of star formation. By studying jets, we gain insights into the feedback mechanisms that regulate the life cycles of galaxies. In the broader context of cosmic evolution, jets are a testament to the dynamic nature of the universe. They are a reminder that even in the seemingly empty reaches of space, powerful forces are at work, shaping the cosmos in ways we are only beginning to understand. From their origins in the accretion disks of newborn stars to their far-reaching effects on the interstellar medium, polar jets are a microcosm of the processes that drive the evolution of stars, planets, and galaxies. The mysteries of polar jets are far from resolved. Each new discovery raises new questions, challenging our assumptions and pushing the boundaries of our knowledge. Yet, this is what makes the study of jets so compelling. They are not just objects of scientific curiosity. They are windows into the fundamental processes that govern the universe. By unraveling the secrets of polar jets, we not only deepen our understanding of star formation but also gain a greater appreciation for the interconnectedness of all things in the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.